Thank you. Thank you. This session is a little bit more technical than the talk this morning. So I am going to be talking about sort of design level tech. There'll be a little bit of code. So if you're frightened of code, go to one of the other sessions. But I think it's understandable by people that aren't developers every day. So it's that kind of level of technical. It's not deeply technical. So I want to talk a little bit about the practice of acceptance testing. And here's the diagram I tend to use as a map of a deployment pipeline. And so what are we talking about with acceptance testing? So first of all, we're talking about automated acceptance testing. This is I'm not talking about manual user acceptance testing or anything like this. This is just about test automation. And you can probably consider pretty much all of the stages, any testing stages after the commit stage has been a form of acceptance testing. But the bit that I'm really interested in is this bit, which is the bit that talks about validating that the software does what the users want the software to do. So that's kind of the theme of all of the rest of this talk. So what is acceptance testing? So first we want to assert that the code does what the users want it to do. We're trying to look at the software from the perspective of an external user of the system. And we want to do that evaluation in lifelike scenarios and lifelike production-like environments. We want to rehearse not just the behavior of the system, but its configuration, the deployment of it, the dependencies that define the environment in which it operates, all of those things. And we'll talk about all of that in more detail. One way of thinking about this approach to test-driven development, which is variously called BDD, acceptance test-driven development, and a variety of other things, is it's kind of like an automated definition of done. If you're familiar with Scrum as a development approach, then Scrum talks a lot about needing a definition of done to say when you're finished. And this is one thing that kind of helps with that. So one of the practices that I quite enjoy is you set up your development team so that for each requirement, you have a user story. For each user story, you have some acceptance criteria that define what it means for that story to be complete. And for each acceptance criteria on a story, we have a team rule that says we will write a minimum of one automated acceptance test for every one of those acceptance criteria. That's quite a nice way of making the problem of figuring out what to test less complicated. It has the slight drawback of meaning that some paths through your system you will over-test, but hardware is cheap compared to people, so that's not a bad deal. We want to assert that the code works in a production-like test environment. So it's no good having it really, really fake. We want, there's the skin in the game here, as the English or the Americans saying. We want to really evaluate this in lifelike scenarios, in lifelike test environments, where so that we're rehearsing the sorts of things that might really go wrong with our software when it's live. And we want to test the deployment and configuration of the whole system. This is about evaluating all of the aspects of the system, not just the bits of behavior that we encode in the source code of our favorite programming language. It's about the way in which we configure it, the way in which we specify the hardware and software in which it operates. It's about all of those things. And we want to provide timely feedback on stories. We want to make sure that we learn what the bad things are before we're in the situation of the guy on the rope of being in a rather difficult place. We want to learn quickly, as soon as possible, if we've made a mistake, so that we can fix it quickly and efficiently. This is kind of about. This has various names, this approach, and I've mentioned some of these already. We're talking about acceptance testing. Acceptance test-driven development is a term that's often used in this space. BDD, behavior-driven development, is kind of one flavor, one approach to this kind of thing. I kind of like the idea of So Specification by Example is a good book on this topic, but I kind of like the idea of executable specifications. This is not really about testing. This is much more about defining an executable specification for the behavior of our system. I'm aware of one organisation, not an organisation that I've worked with personally, but it's an airline, and they write automated tests in a way that they're very readable to human beings. We're going to talk more about that through the rest of the talk. But they write it in a way so it's very readable, so they can generate human readable specifications for the behavior of the system from the test cases that they execute against their system. They've taken this to the extent where their support organisation uses this while they're on a call with a user as the documentation of what the system actually does. At this point, they know that it's correct. They know that this version of the system does precisely this thing because this thing in front of me was a test that was executed against this version of the system and passed. So it's a very strong statement if you think about it in those terms. So I like to think that a good acceptance test is an executable specification for the behavior of the system from the perspective of an external user of the system. And if we go back to my picture that I showed you earlier of kind of a high-level picture of the feedback loops in a software development process, this is the one that we're talking about. We're talking about the one that's kind of a bit coarser-grained than TDD and slightly less than the level of a feature that you're going to deliver to a user. So what's so hard? Why is this a difficult thing? Well, what tends to happen, so many organizations over the years have tried to automate testing for the systems that they're delivering. And these sorts of functional tests are difficult to get right. And what often happens is that the tests break when the system under test changes. This is a coupling problem. This is a problem of software design, and fundamentally, this is what this is that the tests that we write are too tightly coupled to the system under test. So we need to think about that and find ways of fixing it. The tests tend to be complex to develop. They tend to be hard to create and hard to manage, and as well as hard to live with. And the history is littered with poor implementations of this sort of stuff. I have a particular hatred of the UI kind of point and click record things because they're so fragile. You kind of move things around and the tests break, or you change the name of something and the test breaks. So all of these things I think are kind of anti-patterns and things that we should be aiming to try and avoid in our automated testing strategy. I think it's good to think about who owns the tests. And I think it's a nice property from a team point of view that anybody can create a specification for the behavior of a system. Anybody can create a test case. But the people that are going to break the tests are software developers. And so they are the people that need to be in a position to recognize when they've broken their tests and fix the breakages. This last thing, having a separate QA team owning automated tests, is a poisonous anti-pattern that's kind of infected our industry for as long as I've worked in it. I've been working in software development for more than 35 years, and I have not once seen that work. What tends to happen is that you have a group of QA people that are responsible for the automated testing, and you're starting off early, and they'll write some tests while the developers are writing some requirements, and you'll get something up and running, and that'll work. And then the developers keep on changing things, and they'll break the tests. And then the QA people will try and fix the tests. Meanwhile, the developers are breaking more stuff. And you spend the rest of history with the QA team chasing the development. There's usually more people in the development team than the QA team. And the rest of history, the QA team are chasing the developers. So what we will really want to do is two things. First, we want to slow the developers down. And second, we want to make them stop and think about the implications of the choices that they make. If the developers are forced to pause when they break a test, one, that kind of slows the cycle down. which clearly doesn't sound like a good thing, but from a process terms it kind of is. But more importantly, they are going to be the best place. They've just made a change, they've just committed it, it's just been evaluated, it's just failed. They're going to know what's going on. They're going to be able to figure out how to fix this more efficiently than anybody else. So I would argue very strongly that the developers, as soon as the tests start running, the developers own the responsibility for them. This was one of the first ideas that I introduced in a team that I would think of as being kind of a continuous delivery style idea. And it was enormously valuable. Immediately, we went from having a situation of having a whole bunch of automated tests maintained by a QA team that never worked, to having a bunch of tests that were delivering value. So I recommend this very strongly to you. The rest of the talk, I kind of want to go through this list of properties of acceptance tests and talk about each of these in detail and kind of explore the idea. So first off, the properties of a good acceptance test, to my mind, are that we want to be able to express what it is that we want the software to do, not how it is it does it. And that's really common if you look, combining those two, technically conflating those concerns, is very common in approaches to automated testing. Ideally, you want to separate those out. A good mental model for this is if you could imagine, so let's assume you're testing through the user interface. If you could imagine throwing that user interface away and replacing it with something entirely different technology, instead of being a web-based user interface, it's a thought-based user interface. And if your tests could stay running, if they still describe scenarios that made sense in both of those contexts, you've got the abstraction right. We want tests to be isolated from other tests. As we adopt this kind of practice, we're going to write more and more of these tests, and we're going to end up probably with thousands, maybe tens of thousands of these tests that we want to execute. If we want to do that and have rapid feedback, if we want feedback in under an hour, we're probably going to need to parallelize these tests. We probably need to run them in parallel. So we want these tests to be able to safely run alongside a bunch of other tests and give us consistent results. We also want them to be repeatable. We want to be able to run the same test over and over again and get the same result every time, because that makes it easier for us to debug the tests and figure out what's going on. Using the language of the problem domain helps us with several of these things, and I'm going to go into a lot more detail of what I mean by that as we go through, but this allows us to get the abstraction right. It gives us a starting point to be able to do what I just said. If we can express a test in the language of the problem domain, not in the language of the system that we're designing to solve the problem, then usually it gives us a better chance of being able to replace our web-based user interface with a thought-based user interface and it still work. And we want to be able to test any change. Whatever the nature of the change, we'd like this to be an experiment that we can carry out. We'd like to be able to evaluate that change, whatever its nature, with an automated test. And finally, we want to be able to run thousands, maybe tens of thousands, maybe more of these tests and get an answer in a reasonable amount of time, so we need them to be efficient. So we need to think about the efficiency of the tests as well. So let's walk through these properties one at a time and think a little bit about what each of these things may mean. So here's a representation of a system. The actual details of what these things represent doesn't matter very much, but this is from the LMAX trading system that I talked about, but that doesn't matter very much. In this example, what he's trying to demonstrate is that we've got the boxes at the top are kind of communities of users. These are areas, roles that users play. The boxes connected to the bus at the bottom are kind of the channels of communication that those users use to interact with the system. So typically for a system like this, if we were going to write automated tests, what we'd do is that we'd replace the users, the interaction with a bunch of automated tests that interact with the system. In this scenario, let's say we make a change to one of those interfaces in one of those channels. The fix API is It stands for the Financial Information Exchange Protocol. It's a standard-ish that's used in the finance industry for exchanging information between different companies. But as I say, the detail of that doesn't matter. It's just a channel of communication. If you're not familiar with it, if you think of slightly faster HTTP communications, you're not a million miles away. But, you know, so we've got this channel of communication, we've got a bunch of tests written against it. In that scenario, if we make that change that breaks a bunch of tests, the only thing we can do to fix all of those tests is go to each test one by one and fix it. It is slow and inefficient. So how could we solve that problem? Well, the usual solution to that kind of problem in software is that we raise the level of abstraction and introduce a level of indirection. So instead of the users, let's imagine that in our test framework, we embody a placeholder for those communication channels. So now, when our fix API changes and breaks all of those tests, we've got a piece, a component that represents that channel of communication that all of the tests talk to. There's a difference, there's a change in abstraction between the test cases themselves and the interaction with the system under test. This is the same pattern as a device driver. This is like a device driver for testing. So, you know, if you're using Windows or a Mac OS or something like that, you don't have to write a Windows, a printer driver for every printer that you want to talk to. You write something, you have plug and play printer drivers. This is the same idea for each channel. So if one of these tests says place order, and that's going through the fix API channel, the fix API channel knows how to translate a place order into all of the fix semantics for sending a message. If you want to say place order through the user interface, it knows to fill in some fields and press some buttons and stuff like that to place an order. And that's what we're trying to get to. Now, if we just fix the fix API, that fixes all of the tests. So we've scaled up our ability to stay on top of change by changing the level of abstraction. We've simplified things. When you start going down this route, what you find is that you quickly build up a series of assets within your test framework that you can reuse between lots of tests. Place order may be a common concept in your problem domain that you want to do lots of times in lots of different test cases, so you can use that place order abstraction over and over again, and it's simple at the level of the test, and the complexity of how you translate that into interactions with the system is a separate concern, and we architect our test infrastructure that way. And you find that you kind of build up these components and tools that allow you to do this kind of thing as you go forward. So, if we're trying to specify the what, not how, one of the common things that's recommended is every test should control its start conditions. In general, I think that's a really good principle. But the next bit, and so start and init the app. The problem with that is if we want to run tens of thousands of test cases, that's expensive because starting an application is a relatively expensive process. And so if we incur that for every test case that we run, we could do better. What would be nice would be able to start the application once, run a lot of tests against it, and then throw it away after we've got a result. That would be more efficient in terms of the use of our resources. So we could separate these things. So instead of allowing each individual test case to control the starting of the application, I recommend that you start by having that deployment and the initialization of the application as a separate step from running the test cases. In the case of acceptance testing, not in the case of other forms of testing. So you start the application up and then you start running the tests. So the tests start from the assumption that there's a running application. Now, that starts to get into the isolation stuff, which we'll talk in more details in a minute. But this gives us the opportunity to be able to parallelize in the future and run things more efficiently. So let's look at isolation. So I would argue that any form of testing in any domain really is about evaluating something in controlled circumstances. And so we want to be able to establish and control the circumstances in which each of our tests operates. And for that, I think that thinking about test isolation is an important part of that process. And there are different kinds of levels of isolation that come into play. So we can think about isolating the system. So what's the scope of the system under test? And we can think about isolating test cases from one another, and we can think about isolating test cases from themselves so we can run one test case after another. So let's look at the first one first. What's the scope of the system under test? This is largely a scenario recommended in large organizations, enterprises and so on. And often what you will get in enterprises like this is you'll get the recommendation, let's imagine that we are developing system B, okay? And upstream of system B is another system looked after by another team somewhere, system A, that provides inputs to system B, and downstream is system C that takes the output of system B and does some stuff with it. Now, what organizations with stuff like this will often say is you've got to test all of it together end to end to make sure it all works together. And there's a problem with that, because if you're trying to evaluate system B and you're doing that by driving system A, you have a limited degree of control. You can't really be very precise about getting system B into the state that you want it to be in to try out things. Let's say you wanted a test that found out how system B worked when the communications was flaky or down between system A and system B. What happens then? Or you know, what happens if if system C has crashed altogether? What happens then? You'd like to be able to simulate all of those behaviors and find out what happens. Worse than that, if you're working on system B and you're driving it through system A and collecting results from system C, you probably don't know all that much about system A. It's enough to understand the system that you're working on without having to understand everything about all of the other systems that surround it. This way lies madness, because the extrapolating to absurdity, you've got to understand the whole internet to write any system. It makes no sense. So we need to isolate, we need to contain, we need to describe the boundaries of our system. And I think that what we really want to do to get our system into a known state for testing is that we want to write tests as close to the system as we can. So what we really want is that we want something more like this. You want test cases talking through the natural interfaces to the system under test, but test cases as close to that system as you can get them. So you replace the interactions with these higher level test cases. Now, there's a good reason why these big organizations worry about this problem. They're worried about the interfaces between system A and system B and system B and system C. And that's a valid concern, so we need to find a way to validate those interfaces as well. So my recommendation is so we do the test cases and the evaluation close to each of the systems, and then we repeat that for each of the systems. Now, in the context of Team B working like this, what Team B cares about System A and System C is actually quite small. So the number of test cases that you care about for those systems is relatively tiny. You just want an assertion that their interface hasn't changed to the level that you care about their interface. A step beyond this is that you write these tests, System B team writes the tests that assert what it cares about of the interface from System A and the interface to System C, and then it gives those tests to the other teams, and they run it as part of their continuous integration cycle. Then if they make a change, if System A team makes a change that changes its interface that System B cares about, it fails the test in System A's continuous integration cycle and tells the team that they've made a change. And then they've got to figure out, talk to Team B or to tell them to fix something or change what they've done, whatever it makes sense. So much of what I'm talking about is really kind of focused on multi-user systems, particularly the stuff about sharing an instance of the system between different test cases. If you're writing a standalone one-user application on an iPhone, maybe this is different. Maybe you do need to start up the system for every test case. But that aside, most of the systems I end up working on tend to be multi-user systems in one form or another. So we want to assume multi-user systems, for these purposes, we're going to assume multi-user systems, and we want the test to be efficient so we can run lots of them, maybe tens of thousands of these in under an hour. And so we must avoid any dependencies between tests. We must find a way to be able to share a version of the system and run multiple tests in parallel against that system that don't interfere with one another. A really simple way of doing this is to use something I call functional isolation. So it's using natural structures in the code to isolate test cases from one another. So in this example, if you're testing Amazon, you create a new account and a new book for every test case that you run, pretty much. If you're eBay, you create a new marketplace and an account for every test case. And if you're testing GitHub, you create a new repository and an account for every test case. So every test case kind of starts by creating an account and whatever else it needs to isolate it from everything else. That way you've got quite a lot of control. Now this is kind of one of those 80-20 rules. This works for the broad case, this works for most cases that you come up with, but there are going to be some awkward cases that cross the boundaries between some of these things, and you just need to think harder when you hit those. But this is quite a good technique for being able to quickly have a level of test isolation that gives you a good level of parallelism that allows you to move on. So we also want repeatable results. We want to be able to run the test case and have it isolated from itself. So here's a cheesy example. So let's say I've got a store and I want to create a book called continuous delivery, and I'm going to place an order for the book and I'm going to assert that the order was placed. That's my test case, okay? So what's the problem with being able to run this? Well, the first time we run it, this is the line that I think is the problem line. So the first time we run it, probably in our system under test, somewhere, however it stores data, it's going to end up creating a book called continuous delivery and store it somewhere, okay? Now, if we run that test again, we're in different circumstances. Continuous delivery book already exists. Maybe its state changed. Maybe we had another test that changed its price. All of those things. We're now kind of messed up. So what could we do? Well, instead of creating a book called continuous delivery the first time, let's create a book called continuous delivery 1, 2, 3, 4. And then the next time we run it, we'll create a book called continuous delivery 6, 7, 8, 9. We build aliasing into our test infrastructure so that within any given execution of the test, it will maintain a mapping between the token, continuous delivery, and the instance, continuous delivery 1, 2, 3, 4, for any given test run. So within the context of a test run, we can use have the same test run over and over again and still be isolated from versions of itself. Again, this is really, really simple. It's not a terribly complex thing to do, but if you build it into your test infrastructure, you can reuse it over and over again. And I would recommend that you do this pretty much for all of your functional isolation entities, and it gives you a great deal of flexibility in being able to maintain isolation for your different test cases. We want our tests to be repeatable, and this is kind of back to talking about the scope of our testing. So let's imagine that we have a system, and let's imagine that we learnt to program not from Visual Basic for Dummies, but something a bit better than that. And so we're probably going to have a level of abstraction, a separation of concerns between talking to our external system and the model of our system itself. So we have one piece of logic that kind of represents the business logic of our system, and another piece of logic that represents a translation to the outside world. And probably we're going to have another layer here. There's going to be some communication protocol between the external system and the system that we're under test. So the purple bits are kind of the scope of the system under test. The blue bit is the technology that we use to talk to the system under test, and the I don't know what that is, cyan bit maybe, at the bottom is kind of an external system that's talking to our system. So if we've got this separation of concerns, then it's fairly easy for us to plug something in through that natural communication channel instead of the external system. And we can do that via configuration, and now we're able to have the scope of the system that we deploy in our test environment is entirely the system as it will be deployed in production, but we plug in stubs, fakes for external dependencies that we can now control. We take this a little bit further, so here's our system under test again, and here's the stub for our external system, talking through the natural interfaces. There's probably some interface to the logic here. Here's the scope of the system under test. And then we have our test infrastructure and some test cases. What we'd like to do is establish a back channel from our test infrastructure to that stub, so that now we can talk to the stub within our test cases. We can say things like, we expect you to see this result, this output. Or we can say things like, fake this return value. Or we can say things like, place this order through this channel. And it will come into our system under test through its natural interfaces. So there's no cheating here, but we have within our testing, we have control. Now, an awful lot of this becomes an awful lot easier if you start using the language of the problem domain. A simple domain-specific language solves lots of these problems. So it gives us ease of test creation. It allows these tests to be readable, so anybody that understands the problem domain, whether they're technical or not, can understand what the tests are expressing, which is important if you want to understand what you're actually testing. And it gives us a separation from the what, not how. It gives us a very clear line between what we want to express in our test cases and how we want our test infrastructure to interact with the system under test. And it gives you the chance to set up complex scenarios. Now, I apologize, I know the code isn't very readable, so, I'm just trying to show you some simple cases. I think the slides will be available afterwards, so hopefully you should be able to see these in a bit more detail. But this is an example, this is a real example from a real domain-specific language. And basically what this is talking about, if you can read the words, this is saying we're going to select a thing called a deal ticket, which is part of the user interface. We're going to place an order. We're going to check for a feedback message, and we're going to dismiss the feedback message, place another order, and check for another feedback message. So you could imagine a product owner, or even a user of the system, understanding this scenario. It's not really very technical, it's not really very complicated. Underneath, there's a lot going on. Here's another example. This is through, so the first one's through the public user interface to a system, the second one's through the Fix API. I think of REST, it's close enough. Here's the setup for this. So we're creating some accounts, and we're creating a market in which to trade as part of our functional isolation. Behind the scenes, our domain-specific language is doing more for us. So behind the scenes, in the first example here, we've got when we're placing the order, we're just specifying two values. We're specifying a type of order, a limit order, and we're specifying a bid that we're going to buy a certain quantity of things at a certain price. Behind the scenes, this is, behind the scenes, what's going on is that we're putting lots of default values in. So we're specifying just two values, but we're putting lots of default values in behind, and so we can express very precisely what we want of our order under test, or we can just be, we don't care, we want to place an order, we don't care too much what it is, we just need an order, and we can do either one using this approach. We kind of started from, we kind of worked on this for a while, and the bulk of our test looked like this. And after a while, we realized that this didn't really fulfill our test. If we wanted to translate this from the user interface to some other interaction, They were too different. We were too obvious about the difference in channels. So this was the first red bit is describing that this is part of the user interface. The second red bit is talking about this is part of the fix API. And we ended up with this. So this test, this one test, could be run against either the fix API, this financial industry standard, either through the user interface or through the public binary API. One test, multiple uses, because the abstraction's right. I have a client who's re-implementing one of their products, and they're trying to build what was a monolithic product into a microservices, distributed architecture, and all these sexy new things. What they're doing is they're using this approach. We've built tests that assert the behavior of their existing system, and that's valuable in its own right because that system is still under development, but they can plug in a different device driver level thing, and they can run precisely the same specification for the behavior of the system against the new version of the system and see that they match, which is quite a powerful idea. We want to be able to test any change. Come on. So our test cases need to be deterministic. And one of the difficult cases for determinism is time. If you care about time in the scope of your application, time often is a pain within the scope of automated testing. And basically, I think that there are two strategies. You can either ignore time if your system doesn't care very much about time, or you need to take control of it and treat it like an external dependency, the same as any other. In the first case, basically, if time's not very important, you can kind of blank out any field that has a time in it and just ignore, when you're comparing, is this interaction like this interaction, you just ignore the time fields. It's okay. It's very simple to do. It can miss errors, and it prevents any hope of testing complex scenarios. So the alternative is to take control of time. And you treat time as an external dependency and fake it, basically, within the scope of the application. This is very flexible, very powerful. You can run long-running scenarios in very short periods of time, and the downside is it's slightly more complex in terms of infrastructure. So here's an example. So again, it's a cheesy example. Let's imagine we've got a library. We're going to borrow a book called Continuous Delivery. We're going to assert that the book is not yet overdue. We're going to time travel forwards 1 week, and we're going to assert that the book is still not overdue. We're going to time travel forwards 4 weeks. In the UK, at least, you're overdue if it's over 4 weeks. We're going to time travel forwards 4 weeks, and we're going to say it's now overdue. So that's quite a powerful technique. And it's the time travel bits that I'm interested in here. So let's have a little picture of that. So here's our system under test, test infrastructure, test cases. And typically, if we're interested in time, at some level, it devolves to something like this, where we're going to call out to the system to get the time. Okay? So again, we probably want a level of indirection between us. So let's introduce the concept of a clock within our system, and our clock now stands between the system time and our uses of the system time. Now we're in a position where we can cheat. We can talk to the clock, and we can change the time that the clock thinks it is. We can programmatically redefine time within the scope of the application. And again, we establish a back channel of communication somewhere in our test infrastructure that allows us to write in our domain-specific language, time travel, something or other, communicate via this back channel to the system under test, which changes the time as far as the clock is concerned. Other kinds of tests, there are different sorts of things that we can be concerned about. So maybe we want to test time travel tests, destructive tests. Maybe we want to test a particular piece of hardware. And for those tests, we might want to be more selective about the environment where we place these things. If you're doing time travel tests, you can't really run those in parallel with other tests, because if one thing is time traveling, moving weeks forward, and another thing is time traveling, moving minutes forward and something else is not time traveling at all, it's really going to screw up the results of those other tests. So in this case, we do want to have one system per test. So these are more expensive tests. Also, destructive tests. We might want to kill parts of the system and see what happens when they come back alive, that kind of thing. And it's quite good to kind of tag our tests, annotate our tests and say, this is this kind of test. And that gives us the flexibility then to have a test allocator that can make decisions at runtime and decide where to place tests. Here's a little animation from the LMAX project where I worked, created by a friend of mine, a colleague of mine, Mark Price. Mark Price was building the allocator, the test allocator that would allocate tests to run in our test grid. And he did this little visualization to see what's going on. On the far right, you can see that there's one instance, the central little host, and lots of tests running against it. That's the shared one. That's the one that we're kind of starting one and running lots of test cases. The big one on the left is a time travel tests. Each time travel test has its own instance of the application, and it's running those up, and then it will give the host back to the allocator, and then the allocator will reallocate a new test to that host. And at the bottom are sequential tests of other kind, where we're doing the destructive testing. These are tests that could only run in one version of the, need a dedicated version of the application. Finally, we want our tests to be efficient. We want to be able to run tens of thousands of these tests and get a result ideally in a short amount of time. Part of efficiency is trying to make sure that we make the most out of our hardware. If you're Google, you can't afford to have twice as many servers for testing as you have for production. You need to be more sensible than that, but it's really very important in these sorts of tests that we are evaluating the software in lifelike circumstances. We need to be precise. We need to be testing the deployment of our software, its configuration as well as its behavior. And so we want the test environment to be representative of production. Now, mostly what that means is you probably need to care about the same sorts of dependencies, the same level of operating system, the same level of database, the same language, the software that you're putting. You want to rehearse the deployment mechanism, you want to rehearse its configuration, all of those things. So maybe process boundaries too are kind of a key attribute of the system. So if your typical interaction through your system looks like this, then your test environment probably looks something like this. It's just whatever it takes to represent things that can go wrong at the point at which you deploy it and run it in production. If you've got a separate piece of hardware and that's another thing that can go wrong, and your typical interaction or some interactions look like this, then maybe this is your test environment. One of the things with modern systems is that we're increasingly going towards more asynchrony in our systems, and I think that's a wholly good thing. I'm a big fan of reactive systems and very high performance microservice architectures which take asynchrony as a fundamental principle. But one of the complexities with that is the complexity of asynchronous programming and all the race conditions that can happen. From the perspective of a test case, we want to be able to have one line in our test case, go and do whatever it takes to evaluate that line, and then return and then move on to the next line. We don't want to conflate the problems of writing tests with the problems of asynchrony. We want to hide the asynchrony in our test infrastructure. So a good way of doing this is to have a concluding event. There's nearly always an event that happens afterwards that you can kind of trap and understand. So as an example, let's imagine inside our DSL that we have an asynchronous call to place an order of some kind. And then what we do is that within our implementation of the DSL, we say, wait for the order confirmed message or fail on timeout. And then we can kind of write that place order instruction in a test case and not worry about it too much. We can hide the complexity of the asynchrony in our test cases. One of the reasons that I'm mentioning this at all is because I'm trying to suggest that it's a really, really bad idea to put wait statements in your tests, which is really common, because all that does is it slows things down and makes the recovery even more unreliable. If you do all of these things, it means you can scale up. So you can now start to think about the sorts of things that I've talked about. You've got the isolation right, you've got the abstraction right, and so you can get a release candidate in your artifact repository. When the acceptance test environment comes free, it's going to automatically deploy that into the acceptance test environment, the production-like acceptance test environment. The acceptance test is then going to spin out a bunch of test hosts to run tests against that, collect the data, and report back. And that becomes easy if you've got the abstractions and the isolation right. I'm going to whiz through these because I've run out of time, but these are just repeats of the things that I've already talked about, really. So that the don'ts of the approach. And here are the do's, the things that work. Again, I'm not going to read them all out because we're out of time. And with that, I will conclude. Thank you very much.